So today we are discussing MOT only then. Okay. So you're going to be having MOT being of course called as molecular orbital theory. So now what is the idea over here? Why do we have a separate theory now when VBT was working quite well? VBT has certain problems, valence bond theory has some problems over there. Some of the problems associated with VBT mainly come with one aspect over there. See, just like how Newton's gravity is going to be having a problem only when very accurate measurements are being done, like in the case of the sun and Mercury orbit, why it is slightly wobbling. And then we had to come up with another theory to basically patch up Newton's gravity slightly. VBT has some small problems also. Yeah, VBT is actually based on mathematics only to a good extent, and mixing of orbitals, hybridization is properly based on mathematics. One of the small problems is this got the magnetic character of O2 molecule partially wrong. It was not able to explain the magnetic character of an oxygen molecule. In a sense, it was not able to explain it properly. So this particular problem associated with this was one of the main problems there. Of course, there are also certain other things which could not be explained by this here, mainly odd electron molecules. There were a few other problems with VBT also, but yeah, let's continue on with the aspect of MOT now. So all of these small problems, the 2-3 small problems which are there with VBT over there, they basically led to the ideas associated with MOT to come out over there. So let's quickly discuss the idea associated with MOT over here. So when it comes to molecular orbital theory, let's quickly touch upon the part which we discussed about atomic orbitals earlier. When we talk about an atomic orbital, what does an atomic orbital mean? Atomic orbital is basically going to be the bound space within which the probability of finding an electron is going to be maximum. So when we say probability of finding an electron is going to be maximum, the idea there is we are now trying to come up with an equation representing the electron in that space. But electron is basically something which is going to be one of the smallest of particles. So technically you can think of it as an equation for a space itself. So how we are going to be now looking at things is we are going to be considering space as a mathematical entity, and we are going to try to come up with an equation for it. How do we come up with an equation for it? By putting one electron over there, and the wave nature of the electron, we now write the equation for the electron over there. So that basically becomes the equation for that particular space over there. So an orbital, an atomic orbital, is effectively going to be a mathematical equation which represents a space, a defined space inside an atom. So this is going to be what an atomic orbital represents. And what does it continue on? Basically, it basically also adds on to the fact that probability of finding electron is maximum in this space. That is the idea here. So if you are going to be looking at a nice big complex, apartment complex, then you're going to be having certain rooms, correct? You're going to be having multiple flats, multiple rooms, all of those are there. But in different rooms, you'll have different probabilities of finding a particular person over there, or any one person over there. So basically, the person over here represents the electron here, and you can imagine that this is a mathematical equation which is going to be representing that particular space. And in that particular space, the chance of finding an electron is going to be very high. Now, usually, what does this maximum mean over here? We define the maximum as a percentage. It can be 90% to 95% usually. Different books will basically give you different aspects there. Now, when it comes to molecular orbital theory, what are we really having happen over here? So effectively, now when it comes to molecular orbital theory, there are certain problems with VBT here. Mainly the problem comes from O2 molecule, which is going to be a diatomic molecule. So your MOT started off with trying to see if there were some ways to explain diatomic molecules and their magnetic properties and some of the discrepancies with VBT more carefully. So That is where we start off with. So when it comes to a molecule, what is a molecule going to be? A molecule is basically going to be something where you're going to be having a simple diatomic molecule. You're having two atoms combining to basically become a new entity called as a molecule. So when the two atoms are combining, what is exactly happening is you're having two states combining, all right, or two countries combining, or something of that sort, two regions combining. That is one way to look at it. So when you're going to be having two large regions combining, basically you can imagine it as two different spaces combining. Obviously, the space which is going to be in between or shared space between those regions is going to be facing more what to say, attraction in this case here, because the nucleus are basically going to be at two different centers. But that is for the later part there. Let us now talk about the idea behind how this combination of space works mathematically. So when you're looking at the spaces associated with the two atoms combine with each other. So when we say the space associated with the two of them are going to be combining with each other over here, what does that really actually signify over here? Or how do we mathematically proceed over here? See, till now we have defined the space inside an atom based on dumping one electron over there and then finding the equation associated with that electron. That is what an atomic orbital is. And when it comes to mixing of these spaces over here, what happens is we can basically now try to understand, and we have to define space more carefully now. So when we are trying to define space more carefully, the problem which comes up is, how do we define space? Till now we have put one electron in it. Now though it's going to be a molecule, we are going to be having none of the one electron type of thing being applicable here. We have to basically put multiple electrons over here. Definitely we can't really look at it just from mathematical point of view, because mathematically speaking, how did we define space? We had defined it by throwing one electron into that location and finding out the equation of the electron as a wave there. That is what we called as atomic orbital. But when it comes to multi-electron systems, every individual electron is going to be having its own equation associated with it, and it will be different. So it will have interference with other electrons which are present in the system also in the same atom as well. So when you're going to be looking at a molecule over here, we'll have to go more careful over here. We'll have to actually define space more carefully. So how we define space now is like how I discussed it earlier in one of the sessions with you. If we are going to be having, say, the space between my hands to be defined, this space can only be realistically mathematically defined as total universe minus everything else will be basically this space over here. So any space which we wish to define is going to be something which we have to define from a complementary perspective. In a sense, this space has to be defined now, this system has to be defined, means we'll have to define surroundings. Because what we know is only total. Space is going to be always total. We consider it as a totality from mathematical perspective. Then we subtract and we get this individual space in the middle over there. So when you're going to be considering definition of a particular molecular orbital, all right, a molecular orbital is going to be a space which is going to be bounded in some way or another. All right, or it could be something which is bounded mathematically. Some way or another is mathematically only. There is no individualistic, you can't define boundary as between hands or something of that sort. So the idea here is, when you're going to be considering a molecular orbital, the only way to understand molecular orbital is mathematically. And from a mathematical perspective, there are going to be obviously some simple ways to understand it in a graphical manner, because understanding equations is always way too complicated. Understanding things graphically is always much more efficient. That is where the next part of it comes, which is called as linear combination of atomic orbitals. Now, when we are talking about linear combination of atomic orbitals, effectively, to do the mathematics over there, we can make theoretical models, imaginary models to basically understand. But at the end of the day, when you are applying the mathematics, you'll have to do solving of equations. You'll have to sit and combine equations and combine mathematical functions. This is basically going to be the understanding part of it. That is how to define the space as total minus rest is going to be this. That is the understanding concept of it, which will help you in understanding this linear combination of atomic orbitals, which is generally abbreviated as LCAO, in a more efficient manner, so to say. So in this linear combination of atomic orbitals here, what exactly are we going to be discussing? We are going to be looking at taking the standard approximation of what we had solved earlier as atomic orbital equations. What was it? We had assumed one large empty atom which had only one electron, and that electron, if it is going to be in different orbitals, what is the equation for the electron in that orbital or in that space? And because there is only one electron, there is least interference over there, there is no competition, there is no other equations to basically mix with over there, and this is going to be something which is going to be interfering least with the mathematics associated with the equation of the space. That is ultimately Heisenberg's uncertainty principle. When you are having too many observers or too many things you are trying to observe, your observation is not going to be proper. Or if you're going to be trying to observe all the properties of something in a very careful manner, both what its velocity is going to be and what its position is going to be, that is not going to work out, or what its momentum is going to be, what its position is going to be. For the electron over here also, the electron is technically the way in which we are observing that space. So when we are trying to observe space and mathematically come up with an equation for space, the simplest way of doing it is by putting one electron over there. If you're going to be putting in multiple electrons, you will have some kind of interference between them. They are not going to be necessarily mixing comfortably. So you'll have to include any issues which which come up when they are in the same rough location of space, totally speaking. So when it comes to molecular orbital, you're automatically going to be having electrons combining over here. So to understand the combination of electrons, we have to first throw one electron in each of those places, find out the mathematical equation, understand the combination of the mathematical equations, then combine it with some proper chemistry model which is going to be more meaningful to understand what the mathematics means, how can we use this to make our theory better. So coming back to things over here, so in a molecular orbital combination over here, we are going to be using a set of rules which are called as linear combination of atomic orbitals. So let's try to understand how this works out over here. So when you're going to be having an s orbital, any orbital is going to be something where you're going to be basically plotting the mathematical function of psi or psi squared, or whichever mathematical function you wish to plot over there. So usually we'll be plotting psi square, which gives us probability of finding the electron over there. So usually when you're going to be having that, the mathematical function, if it is psi square, it will be fully positive in every direction. If it is going to be psi though, there will be certain parts where there will be a positive and there will be a negative aspect also. So let's say in this particular case here, this entire side is going to be positive, this side is negative. Alright, so this is going to be a typical s orbital. So when you're going to be considering a typical s orbital and you're going to be combining it, let's say this is going to be 1s orbital, if it is combining with another typical 1s orbital, this is going to be something which is very much obviously happening in a hydrogen molecule. In a hydrogen molecule, each hydrogen atom is going to be having the electron in the 1s orbital and it combines with another 1s orbital's electron over there. So you're going to be having in this case here, if you are going to be having the overlap which is going to be happening, if these two orbitals are coming in, then of course you're going to be having the center of these over here is going to be the nucleus, which is also going to be the origin over here, technically speaking. So if these two atomic orbitals are moving in this direction and they are combining with each other, then we end up drawing the final combination of there are two orbitals combined over here, technically two spaces have combined. So ultimately we can assume that some space is going to be formed by the combination, but when we are defining space, how are we going to be defining space? These two are defined spaces. Already defined space. How is it a defined space? It is defined based on the nucleus and one electron being there. Now what are we going to be getting? We are going to be getting undefined space. Space where there is nothing present, where we are mathematically now finding what should be the new spaces formed over here. So any two space when you combine, the logic is, or any number of spaces you combine, you are going to be getting two spaces effectively. One which is going to be including all of the space which is going to be in between type, or if you're defining any space, it is going to be mathematically something which is going to be defined as total minus everything else. That is the way we define space. So when you're going to be looking at the combination which is going to be happening over here, you have one set of orbitals, one type of molecular orbital. We're going to call it as a molecular orbital because it's basically based on combining these two atoms over here. So we'll have one set of molecular orbitals which is going to be called as bonding molecular orbital. Now when it is to be called as the bonding molecular orbital, what is special about this? What is the idea behind this? This is formed by constructive interference. We are now looking at wave nature type of thing. So we are going to be looking at constructive and destructive interference. So constructive interference, now what does it mean? Let's say we are having two waves. When you're going to be having these two, basically the crest part and the crest part and the trough part and the trough part combining, we end up having a wave which is going to be a much bigger wave effectively, with the same plus over here and a minus over here. So you're going to be having this being constructive interference. Destructive interference is if I'm going to be combining this fellow with this guy, let's say. You're going to be having these two now combining to effectively give me a nothing. So in this particular case here, this is called as destructive interference. Basically all we are doing is adding them. Alright, but at the same time here, you're going to be having, in constructive interference, you're going to be having the wave's amplitude directly increasing over here, because you're going to be having the positive and the positive parts are going to be combining, because the phase is going to be in phase. Whereas if you're going to be looking at destructive interference, you can say they are technically out of phase waves. So you're going to be having, this is going to be constructive interference. So this is basically representing that you're going to be having in phase waves, whereas you're going to be having this being out of phase. Basically there is a phase difference, of course, and the phase difference is going to be resulting in them cancelling out each other to a good extent. Okay, so when you're going to be having a combination of atomic orbitals taken here, the bonding molecular orbital is considered as something which is formed by what is referred to as constructive interference. So if I'm going to be considering it as constructive interference here, what will this one look like? This will effectively look like one massive orbital like this, where you're going to be having the two nuclei present over here and over here, and you're going to be having bulk of the combination basically present in between over there. This is referred to as a sigma 1s orbital in this particular case here. Why is it called a sigma 1s? Because 1s and 1s over here are going to be directly head-on overlap only. So this head-on overlap results in a head-on overlap in this particular case. When we are going to be having a head-on overlap happening, that kind of an overlap results in the formation of a sigma bond, whereas sideways or lateral overlap results in the formation of what is called as a pi bond. That is what we have defined according to VBT there. So this is going to be referred to as a sigma 1s orbital in this particular case here. Of course, if I'm going to be having them in opposite manners, in the sense, if I had say the 1s like this, let's say this side was plus plus minus minus, this was combining with say another one here where it is plus plus here and a minus minus like this. So now you can see that this is going to be involving a destructive interference which is going to be happening here. So in this destructive interference, the output which we are going to be getting over here is going to be looking like this. We will have the two nuclei still. These two will be moving in this direction. So we'll end up having one of the nuclei over here, let us say another nuclei is over here. The bond or the orbital's location which is going to be seen now will be like this. So the electron is going to be predominantly present in the green regions over here, which are going to be this region over here and this region over here. It is not going to be present much in between over here. In between space over here, as you can see here, this is the in between space. In the in between space, there is lower probability of finding electrons. In the space which is on the other side, you are having higher probability of finding the electron. So in this particular case here, the idea here is this is going to be forming what is called as a sigma star 1s orbital in this particular case. The star here represents what is referred to as an anti-bonding combination. So this is going to be involving your destructive interference over here. So this is going to be an anti-bonding combination over here. This is of course going to be involving destructive interference in this scenario over here. So we're going to be having sigma star 1s orbital over here. And in this particular case here, you're going to be having destructive interference effectively happening over here. So effectively, the idea here is very simple. When you're going to be having any set of orbitals combining, you will have a new set of spaces formed. How do we define this space which is formed? We define it based on the part which is going to be constructive interference and the parts which are going to be destructive interference. Of course, you can always define it in many ways, because you're defining it mathematically, correct? You can define it as 10% interference, constructive interference, 20 percentage constructive interference, 40 percentage constructive interference. You can make any number of spaces you wish. That is the truth. When you're combining two spaces, you can make 10 spaces. When you're combining 10 spaces, you can make two spaces. It doesn't make a difference because everything is mathematics here. Ideally, why are we taking the final output as two spaces over here? Because that is easiest for us to define a space without throwing an electron into it. Because ideally speaking, we need these spaces empty to confirm if the electron is going there or not. Because all of this is theoretical. This is going to be experimentally known. We know this part experimentally. That is, we have gotten the mathematical equation for an atomic orbital done. No problem. How did we do that? We threw an electron in that space. We basically calculated the mathematics and energy and etc for it. We were able to get output for it. We were able to derive some kind of an equation for it. But this is something which is technically empty. So you can make as many spaces as you wish for the sake of understanding it in a more meaningful manner. Ideally, scientists basically pick two spaces. Why did they pick two spaces? Because they could define space as this and everything else. And mathematically speaking, what was the combination between these two? Everything else plus this should give me 1. That is the idea there, or should give me totality. So based on that, they basically started defining the mathematics of a space equation wise. So yeah, that's why they went with 2. So instead of looking at partial combinations, they just simply decided everything which involves constructive interference is on one part, everything which involves destructive interference is on the other part there. Now, let's try to understand how the various different combinations go for the different p orbitals over here as well. So when it comes to an s orbital and a p orbital combining, as you can notice, we have looked at the probability diagram which we generally end up getting for that particular electron in that orbital. So for a p orbital, the actual general diagram looks like this. This is going to be a p orbital wherein you are going to be having, let's say if this is going to be x-axis, this will be px orbital over here. S orbital is going to be the same as earlier. S orbital is going to be something which is going to be very straightforward like this. So if I'm going to be having plus plus and minus minus in the s orbital like this, let us say this side was plus over here and this one is minus over here. So in this particular case here, you're going to be having a proper constructive interference happening here. Now, why am I showing the overlap like this? I am now taking a case of head-on overlap. Technically speaking, overlaps can happen in any way you wish to basically mathematically go for it. But ultimately, there are some types of overlaps which do happen in atoms when they form molecules. Quite a few do not really ever end up happening. So in this particular case here, what is going to be obtained as product? We have a nice sigma sp bond formed over here. So we are going to be calling it as a sigma sp orbital over here. And what is this sigma sp orbital going to look like? You are going to be having in this particular case here, let's put the two nuclei again, because with respect to the nuclei only we can draw. So let's say we are going to be having this as one nuclei, this is one nuclei over here. We'll end up having in this particular case here, bulk of the electron density will be in this region between the two orbitals over here. So we can say this is going to be the new space which is going to be obtained over here. How do we understand this new space over here? Actually, this is not perfectly correct. A better one would be like this. Better. So the idea here is you're going to be having in this particular case here, this is going to be the combination space over here. The entire part is the combination space which is going to be obtained over here. This is called as a sigma sp over here, and you're going to be having this also as a bonding molecular orbital in this case. Now, why is this a bonding molecular orbital? Because it's involving constructive interference. Why constructive interference? Because you're going to be having plus and plus here mixing with the plus on this side. Now, what is the advantage of having a bonding molecular orbital there? Why is it called as bonding? Why is that guy not called anti-bonding or whatever? The idea is very simple. When it comes to any bonding molecular orbital, yeah, mathematically it is going to be constructive interference, all of that is fine, but that doesn't really give us really any understanding over there, because the mathematics of psi are useless. Psi doesn't have any real meaning for us. So psi is just mathematical equations and graphs over there, so they don't really have any direct meaning there. Bonding molecular orbital though, why is it going to be more stable? Because this is always going to be including the space, or rather this is meant for the space shared between the two nuclei. So when you're going to be considering this as the what to say, space between the two nuclei of the two atoms combining. Now, what is the advantage of having this space over here? This basically means any electron in this space will automatically end up having what over here? If this electron is present here, it will have greater attraction because it is closer to both nuclei. So if it is going to be closer to both nuclei, automatically it will have more attraction from both of them, which will result in greater electrostatic attractions, greater stability. So this is basically the idea over here. It is going to be in this space is going to be having greater attraction. Greater attraction means greater stability. And what else does it also mean? It also means lower energy. Why? Because the energy here is negative. Potential energy is going to be minus, it will become negative over here because Q1 is positive, Q2 is negative over here. So why is this lower energy? Because energy is going to be nothing but KQ1 Q2 by R. And Q1 is going to be positively charged nuclei and Q2 is electron, negatively charged. So this is the idea in this particular case here for the bonding molecular orbital. Of course, when you're going to be considering the anti-bonding molecular orbital, exact opposites are generally going to be applicable over there. It is space away from both nuclei, both combining nuclei. Just both nuclei is fine, which are going to be combining over here. So when you're going to be looking at this is the space over here, electrons in this ABMO are of course going to be having lower stability. Why do they have lower stability? Because they are going to be having lesser attraction, and this of course also means they will be having greater energy. So this is the idea when it comes to combining these atomic orbitals over here. Now when you're going to be having atomic orbitals combining, you have to basically follow the standard rules of VBT to combine the atomic orbitals. What do I mean by standard rules over here? When you're having a sigma bond, that means you're going to be having head-on overlap. If you're going to be having pi bond, that means you're going to be having sideways or lateral overlap. And of course, quite often you will also have no bond. In the sense the two fellows will mix, the spaces can be mixed mathematically, but no bonding is basically formed over there. We call this as non-bonding molecular orbitals. In terms of sigma here, you'll of course have sigma being the bonding form. Sigma star is the depiction which you're going to be using for anti-bonding in this particular case here. Pi also will be having pi being the bonding, and pi star is going to be what is referred to as the anti-bonding type of orbital in that particular case there. Now there are some mathematical properties which will of course have the moment when you're going to be having this kind of combinations and all discussed over here. In the sense, when you're going to be looking at different types of combinations, we have looked at sigma S, we have seen sigma star S, we have seen sigma SP so far, and of course sigma star SP. Sigma star SP is going to be the parts which are going to be not in between the two nuclei which we are combining there. So for instance, in this particular case here, sigma star SP is going to be something like this. So let's say I'm considering sigma star SP here. What does that mean? Let's say I'm having an s orbital combining with a p orbital, say plus and plus, minus and minus. If this is combining with a p orbital over here, where you're going to be having it like this, where it's a minus minus and a plus and plus, the combination will finally lead to the product over here being something like this, where again position the two nuclei, you'll have predominant electron density in the orbitals over here being like this. This will be for one part here, for this other part it will be like this and like this. This is going to be your sigma star SP. Alright, effectively just push them all away because you're going to be having no overlap happening there. So when you're having no overlap happening or very minimal overlap happening because of destructive interference, push everything else to the other side, your job is done. So this is going to be your sigma star sp. Now when you're going to be having the s and p combining in a slightly more different way, when I say more different way here, let me show that out also. If I have the s and p combining like this, let us say, if let's say this side was positive, this was negative. In this particular case here, you are going to be having what is referred to as a non-bonding molecular orbital formed here. What does it mean for a non-bonding over here? This is of course going to be anti-bonding. So what is meant by non-bonding? They do not overlap at all in that fashion, because when you're having an SNP overlapping, they will only perform a head-on overlap and they will not be going for some kind of an overlap in this fashion. Why? Mainly because you are not going to be having any greater attractions at all over here. For instance, if I'm having these two combining over here, what is going to be happening? They'll both come closer. When they come closer, some spaces should benefit more and some space should be less beneficial in the combination of the two. Beneficial parts are going to be what we refer to as the bonding molecular orbital over here. Beneficial in the sense that space between the two nuclei is going to become more and more stable. Why? Because there is more and more interaction there, and the interaction is beneficial in this case here. Whereas in the anti-bonding molecular orbital space there, for whatever reason, the interaction is not beneficial and it is going in the opposite direction. They want to go away from each other. Non-bonding, there is no benefit or what to say problem happening there, which means this will never end up happening. This combination never ends up happening. Or you can think of this non-bonding case as a purely theoretical type of case. It is relatively not much else to look at over here. Okay, now let's look at other types of combinations over here. So we have considered sigma S, sigma star S, sigma sp and sigma star sp. We've also looked at the non-bonding case here. So now let's start looking at pi combinations over here. So if I'm going to be looking at a pi combination here, where we are going to be having pi bonding molecular orbital over here. So pi bonding molecular orbital, now pi orbitals are going to be p orbitals basically, which are going to be combining with each other. So let's say we are going to be having p orbitals combining here, a plus and a plus. Let me put the plus with a different thing. A plus here and a minus here, and a plus here and a minus here. When you're going to be having this basically undergoing a combination over here, what we end up having is, we end up having a nice big cloud over here on top and another cloud over here on the bottom, where this cloud will be plus, this cloud will be minus. The two nuclei over here, we can think of them as being in the center here. So the two fellows are going to be over here and here. So this is referred to as what is called as a pi bonding molecular orbital, and it is of course generally referred to as simply pi BMO. If I was having the combination happening slightly differently, let's say I had the same two p orbitals combining, wherein you are going to be having in this particular case here, let's say a plus here and a minus here, but a minus here and a plus here. In this particular case here, they do not really combine at all. This is going to result in the anti-bonding over here. So what happens in the anti-bonding? Again, first thing, put the nuclei up. When it comes to the anti-bonding, it will basically give a little bit more clarity as to where you'll have to put the remaining things there. Even if you don't remember, you can always make up stuff. So in this particular case here, they are going to be going away. So in this case here, they're going to be going away from each other. Now you can think of it as there will be one lobe over here, one lobe over here, one lobe over here, and one lobe over here. The lobes are going to be oppositely pieced over here. So this will be a plus, this will be a minus, this will be a minus over here, and this will be a plus. So you are going to be having no combination happening. They are just going to be spreading away. This is of course going to be what is referred to as your pi star bond anti-bonding molecular orbital in this particular case here. So when you're going to be considering the different types of molecular orbitals, you're going to be having space combinations basically being looked at over here. Now, of course, you can also have p orbitals. In this case here, p orbital is combining two different p orbitals are combining. We are resulting in a pi and a pi star. But they can also combine to give me a sigma over here. So if the p orbitals are combining in a sigma fashion, that means they are doing a head-on overlap. So head-on overlap is going to be same as the s orbital type of mixing. So let's say plus here, a minus here, and a minus here. Let's say this is going to be resulting in a nice sigma mixing. Sigma mixing means you're going to be having the two fellows over here being nuclei. Let's put them first. You're going to be having plus and plus mixing in the middle beautifully. So you'll have a nice big orbital like this, type of thing with tiny pieces on the outside over here. So you're going to be having, in this case here, this entire thing will be plus, this will be minus, this will be minus. So this is going to be your sigma pp bonding molecular orbital. And if I'm going to be looking at anti-bonding in this case here, how will that be for the anti-bonding? Anti-bonding means I'm combining this fellow with something like this, where I'm going to be having a minus here and a plus over here. So this will effectively result in the product obtained being something like this. You're going to be having in between being very less over here. So again, put the two nuclei first. So in between it has to be very less. So it will be like a tiny thing over here and a tiny thing over here, with a big one over here and a bigger one over here. So you're going to be having in this case here, the tiny thing in the middle over here. This will be a plus tiny fellow over here. Let me put it with, I'll put it as a plus here and a minus here, and I'll have a minus here and a plus here. So this is going to be your pi star, not pi star, damn it, sorry. This is going to be sigma star pp, or you can think of it as, if I'm going to be involving 2p and 2p orbital, I'll call it as sigma star 2p in this particular case here. Specifically, if it is going to be 2px and 2px involved over here. So let's say it's 2px, 2px. Then we'll end up having sigma star 2px. If I'm going to be considering a 2pz and 2pz, I'll call it sigma star 2pz. That's all. It doesn't matter what the mathematics is. The graphical analysis is going to be very useful in understanding things much more effectively than, understanding the mathematical part of it from equation perspective, because equation perspective is basically more easily understood by putting graphs, and that's basically what we are doing over here. So these are the various different combinations involving s and p orbitals over here. You can always have other types of combinations involving d orbitals also. D orbitals, if you're going to be considering them, yeah, sorry about that disconnection. Let's continue on. So when you're going to be having d orbitals here, d orbitals also can be involved in these kind of combinations over here. Same as p orbitals, same rules in terms of bonding and anti-bonding which we have done. Non-bonding, of course, when you're involving an s orbital, then the idea here is you'll have non-bonding orbitals. D orbitals can give you sigma and pi, sigma star and pi star. Same logic as what we have done for the p there. Same type of thing. Put the nucleus first and then figure out how to put the other ones there. Alright, put the nucleus in first and then put the other orbitals, put the other lobes. If you're going to be having constructive interference, make a nice bigger lobe. If you're going to be having destructive interference, just make sure that the lobe basically is going to be not touching. None of the lobes should be touching. That is basically the only rule over there. So now when you're going to be looking at each of these mathematical functions here, d orbitals can also play a role over here, and the same rules apply for p and d, effectively speaking. Non-bonding molecular orbitals, when do you get them? When you're having an s orbital and say a p or d, which is going to be doing something where it's going to be not along the axis where you're going to be having the bond formation happening, which is called as the internuclear axis. So if they are going to be combining in a non-linear fashion, then we end up having, in this particular case here, what is referred to as the non-bonding molecular orbitals usually. So this is the basic mathematical interpretation of the graphs over there. So now when you're going to be considering these graphs over here, these graphs you don't need to memorize. All you have to do is understand what we are doing, how we are doing it, and you can always make it up. So the idea is to understand the logic of how we combine them, and you can just move on, no need to bother. A couple of mathematical interpretations about these which I need to basically give over here, because these are mathematical functions at the end of the day. So when you're going to be having these as mathematical functions, you will have certain properties associated with them which you'll have to basically look at. One of the most critical properties is referred to as symmetrical properties, and whether they are symmetrical or unsymmetrical. Symmetrical means we have a separate name for these orbitals over here. We call them as gerund orbitals. Spelling I'm not 100% sure. It could be GERUND or GERAND. Gerund means the orbitals which are formed, molecular orbitals formed are symmetrical. And of course, you're going to be having which ones coming into this category here. Look at this sigma 1 over here. This sigma 1 here is nicely symmetrical around the center of the molecule. I should have mentioned where it is symmetrical across. Symmetrical along the center of the molecule. Because when you are mentioning symmetry, you have to mention a particular property across which you are checking for the symmetry there. So if I'm going to be considering this fellow here, the sigma 1 over here, as you can see, if I'm going to be considering this as the center of the molecule, you're going to be having it being nicely, perfectly symmetrical around it. In a similar way, the sigma star here, this is not symmetrical around the center of the molecule. This is center of the molecule. This is unsymmetrical. So sigma is symmetrical here. And let's consider the pi fellow here. Let's see how the pi was. So if I put a nice thing in the center here, as you can see, on all four directions, it is nicely symmetrical over here. On the directions over here, just like this one over here, this guy is also nicely symmetrical on the center over here. Both sides from the center perspective, it is looking the same over here. So this is going to be, sorry, not the pi over here. In this case, it doesn't look symmetrical actually. Have a look here. If I'm considering this point as a central point, I should use a different color, I suppose. Let's say I'm considering this point as a central point. In this particular case here, we end up having over here and over here being the same. Over here and over here were the same. So the idea here is when you're going to be looking at symmetry from a center there, you need to draw a line and then see 180 degrees to it if they are going to be the same. So in this case here, if I'm drawing a line across this region and this region, they are not the same because in this case it is a plus over here, in this case it is a minus over here. Same thing over here is not going to be there for the pi star though. In the pi star case, if I'm going to be drawing the same thing and bringing the center up over here, in this central location here, what is going to be happening from this center? This part over here is going to be negative. So if I'm drawing a line like this part is negative, this part is negative. So equidistant from the center. Again, okay, so let's continue on. Small issue with the disconnections needlessly. So if we are going to be considering the orbitals over here, when it is going to be say a pi star type of thing, let's say in this center over here, the idea here is when it comes to identifying center of symmetry, what do? We plot any line from the center over there at equal distance from the center. You should be having same thing, same object being seen over there. Then we can say it is a center of symmetry. So in this case here, the pi is not going to be symmetrical across the center, but the pi star is symmetrical across the center. So we are going to be having, from a symmetry perspective, sigma is working out as a gerund, pi star works out as a gerund. And at the same time, if you are going to be considering the opposite name for it, it is of course called as ungerund, I think. I'm not sure what exactly it is. It doesn't make a difference honestly. Not symmetrical, or the center of molecule is not center of symmetry. Center of molecule is not center of symmetry. That is the idea over here. So you'll of course be having sigma star here and pi coming into this picture here. So this is basically the basic idea over here. Now another piece of information which will be useful. Okay, no need to go there now. We'll directly get into the combinations itself directly now from a larger molecule perspective. So what we are going to be doing now is we are going to be looking at how the different molecular orbitals or atomic orbitals are going to be combining, and what are the new molecular orbitals which are going to be formed from a diatomic molecule perspective. So specifically we are going to be considering diatomic molecule, and we are going to try to understand what are the different combinations which are going to be possible here, and more specifically we are going to be looking up to what to say 2 shells. Alright, up to 2 shells only we are going to be considering from the atomic orbitals perspective. We are not going to be going into the 3rd shell, meaning we are going to be considering only for 1s, 2s and 2p from the atomic orbitals perspective, and we are going to be seeing how the energy is going to be combining there. Now there are going to be two types of combinations which happen over here. I'll just describe what is going to be happening in a nutshell first over here separately, and then we'll go for it. One type of combination happens when we are going to be having molecule with total more than 12 electrons. All right, and you're going to be having another combination happening for less than 12 electrons, or actually you can think of it as more than 12. You can change it to more than 14 over here. It doesn't make a difference actually. So more than 14 is also perfectly fine, and less than 14 is going to be the other combination over here. Now let me start describing a simple case over here for a few simple cases, then I'll describe why that is going to be the scenario, why we are following that. So we'll take a default setting and try to understand it. So we'll be going from lowest energy to higher energy slowly. So if I'm going to be looking at a 1s orbital and a 1s orbital combining, we can represent them as similar energy levels or same level basically. And when you're going to be having the combination happening, they form a sigma bond usually. So we'll end up having the sigma bonding will be of even lower energy, and then you'll have an exact equivalent anti-bonding formed over here. Why will it be an exact equivalent anti-bonding? Because technically we are going to be having conservation of energy being applicable. So when you're going to be having not just conservation of energy, conservation of momentum, everything is applicable. So we'll end up having in this particular case here, this energy delta E here is also going to be the same as this energy delta E here. Both of them are same. Both of them are same in this particular case here. They are not going to be different over here. So they are both going to be equal in this particular case here. And we are going to be having this one being referred to as the sigma 1s, and this is referred to as sigma star 1s. Now next up, when you're going to be combining the 2s orbitals, the 2s orbital is of course going to be at a higher energy level. So what we are doing is we are now technically plotting energy on this axis here. What is happening again? Okay. So you're going to be having technically energy on the y-axis over here, and we are plotting to see what the orbitals are formed are going to be having in terms of energy. Why do we plot with respect to energy? Because when you are now filling up a molecule, we are going to be following the same rules as earlier which we defined, which is Aufbau order, Hund's rule, and of course your Pauli's exclusion principle. All three are going to be applied over here also, because those are universal rules for filling up empty spaces with electrons basically. Okay, so when you're going to be having 2s and 2s combining now, how is that combination going to be looking like? The 2s orbital is originally going to be having a much higher energy compared to the 1s over here. So 2s and 2s will be at a higher level. Again, same type of combination ends up happening. The 2s will also form a sigma 2s and a sigma star 2s. So we'll have this as the sigma 2s and this will be the sigma star 2s. Same way as earlier, we'll end up having this energy difference. Okay, I've not drawn it beautifully properly in this case here. I should draw it a bit better. So at a similar level over here. Okay, so technically speaking, we are going to be having these two energies over here being the same in this particular case here. So we are going to be having these two being same. Same delta E. Let's call it delta E2. So you're going to be having the energy difference between them being the same when you're going to be having the bonding and the anti-bonding of the same type being considered. Why? Because we'll be applying conservation of energy, conservation of momentum. Effectively, mathematically, what is the idea there? This space plus everything else should equal total. So they have to combine with each other, means you're going to be having energy being the same for the total and this plus this. If you're going to be having some mistake happening there, that is not going to be correct in this scenario here. Okay, so these are going to be your sigma 2s and sigma star 2s. Next up, when you're going to be having the next level of energy coming up over here, I'm going to be putting it on this side over here because it is basically going to the other side there. It is more easier to show it on one page. I'm going to now look at a combination of p orbitals right now. So we have done the combination of 1s and 1s. This side is going to be representing atom number 1. This side is going to be representing atom number 2. So when you're going to be combining the two different atoms over here, the 1s and 1s of the two atoms combined, 2s and 2s of the two atoms combined. Why? Because they are of similar energy. If they are of very dissimilar energies, combining them is not going to be applicable. So one of the hidden rules of MOT is only orbitals or atomic orbitals of similar energies combine with each other. If they are of very dissimilar energies, they do not end up combining with each other, or the probability of that combination is going to be very low, so we don't bother with it. So the idea here is only the atomic orbitals which are of similar energies to each other can combine with each other or will combine with each other. So that is something which we are inherently applying in these cases over here. So when I'm going to be inherently applying that over here, what is going to be happening now? We are going to be having three different p orbitals applicable. So what are the three different p orbitals? We are going to be having 2px, 2py and 2pz. So atom 1 and atom 2 are both going to be having three different p orbitals combining over here. So again this will be 2pz, 2py and 2px. So you're going to be having three different atomic orbitals mixing over here simultaneously, because all three of them in the beginning are of similar energies. But you're going to be having the combination of the orbitals over here can result in either a sigma or a pi bond, depending on what is going to be the internuclear axis in this particular case here. Internuclear axis is basically the axis where you're going to be having the two things basically coming along. The two atoms are coming along and mixing along that axis. So when you're going to be considering it that perspective over there, you're going to be generally assuming PZ as internuclear axis. What does this mean? This basically means you're going to be having PZ overlap will be sigma. So we'll have a sigma 2pz being formed and not a sigma of any of the other pz types. So let's say we are going to be looking at the combination of these guys now. How is this combination going to work out over here? So let's put the sigma orbital first. So sigma 2pz, let's put it over here. So this is going to be my sigma 2pz. Let's say these guys are on the same level here. So exact opposite, I should be having the other fellow there. So let me put this as a line here first. And I will have another line over here which is approximately the same amount. So I'll put one more over here. This guy is going to be my sigma star 2pz. So we're going to be having sigma 2pz and sigma star 2pz. Of course, in this case here, this delta E, let's call it as delta E3. This is also going to be delta E3. Okay. Now, in general though, what is the next thing which we are going to be having? Sigma bonds are more stable than pi. Why? Because you're going to be having greater attraction there. Sigma has greater attraction. Of course, if it is going to be more stable, what does that really mean? That also means sigma has lower energy. That is the next part over here to understand. So in this particular case here, if I am now going to be putting up pi orbitals over here, the pi combinations are of course going to be for the 2px and the 2py. These two guys are going to be involved in pi bonding, whereas this was involved in the sigma over here already. So if you're going to be having the pi bonding involved over here, let me put these as sigma with white and pi over here with this color. So these two guys are going to be involved in pi bonding over here. So if I'm going to be having pi bonding forming over here, the pi bonding molecular orbital is going to be having greater energy and lesser stability compared to the sigma. So we are going to be having this being pi 2px and this fellow will be pi 2py. So we are going to be having this as the pi 2px and the pi 2py over here. But same logic, energy difference should be similar. So same higher level over here, same amount you should go up. So we'll end up having pi star 2px over here and pi star 2py over here. So this is going to be pi star 2px and this fellow will be pi star 2py. And of course, in this particular case here, this is going to be delta E4. This will also be delta E4. So this is the idea in this particular case here. So you're going to be having these as the various different molecular orbitals which are formed when you are combining the different atomic orbitals. So which atomic orbitals combinations are we only looking at? We are only going to be considering the combination of 1s, 2s and 2p orbitals. We are not going to be combining anything else. Above that it becomes much more complicated because different levels will have similar energy. Remember, when I say similar energy combines, sometimes we might end up having, say, d orbitals of something having similar energy as s orbitals. So they might also end up having a combination happening there. For instance, 4s and 3d will have similar energies, correct? Or they are having much closer energies compared to 4s and 4p. So you're going to be having the 3d and the 4s also having a chance of combining. So you will have certain awkward combinations happening in that particular case. In fact, we will start seeing one awkward combination in the next level itself. Now itself, in this 1s2s2p itself, we'll see a new awkward combination over here. So before we go into that awkward combination, let's now bring out the off-bow order from this. So off-bow order, what is the off-bow order idea here? Off-bow order, of course, means we are going to be looking at the increasing order in this particular case here of the energy for the different orbitals. So increasing order, we have, first we are of course going to be having sigma 1s, then sigma star 1s, then sigma 2s, then sigma star 2s, sigma 2pz, pi 2px, pi 2py, pi star 2px, pi star 2py, and lastly sigma star 2pz. So let me put this all down over here. So the off-bow order over here works out as sigma 1s, then sigma star 1s, then we end up having sigma 2s, then sigma star 2s, then we ended up having sigma 2pz comes out first, then we have sigma star 2pz as the last over there. So after sigma 2pz we have the pi 2px and pi 2py showing up. So we end up having in this particular case here, next up is going to be, so if I'm putting increasing order, it will be like this. So after this we'll have sigma 2pz, then we'll have it less than pi 2px, but pay attention here, the pi 2px and the pi 2py are of equal energy. Both of these two are of equal energy. So I should put it as an equal to here, meaning Hund's rule will apply over here. So pi 2py, then we'll have that being less than pi star 2px, which is also equal to pi star 2py. And then finally we are going to be having sigma star 2pz. So this is the off-bow order which we have arrived at in this particular case here. Now, when we are going to be looking at where is this off-bow order to be used, this off-bow order is to be used in case number 1. Alright, when I'm going to be looking at case number 1 here, let me put it in a different color. I'm going to call this case number 1. Case number 1 is going to be for systems with, or the diatomic systems, of course, diatomic systems with more than 14 electrons total. That is the idea. Alright, so diatomic systems which are going to be having more than 14 electrons total, you will follow this particular off-bow order and fill in the electrons. Now, I'll discuss a couple of cases for this also at the ending here, once we are about to finish off over here. Now we'll go for the other case here, less than 14 electrons total. This less than 14 electrons case total, I'm going to call it as case number 2. But to understand this less than 14 electrons case and the more than 14 electrons case, let us now bring it down to 14 or less than 14 electrons and try to see it. So if I'm having 14 electrons total, alright, we can think of it as 2 atoms, 7 electrons each, combining. So let's try to understand what the combination or the electronic configuration of this is going to be. 7 electrons each means it is technically going to be 2, 5, which of course works out as 1s2, 2s2 and 2p3. So pay attention here, the combination is going to be 1s and 1s, which is going to be fully filled, no problem. 2s is also going to be fully filled, no problem. But the 2p here is perfectly half filled. Now, when you are going to be considering any system of electrons in this fashion here like this, let's say I'm considering this 2p here. Alright, this 2p orbital over here is going to be having some average energy for each electron associated in this particular 2p orbital over here. So let's say that average energy is to be considered over here. That average energy, let's say I'm going to be considering it as some x over here, or let's call it x1, which is going to be average energy per electron in 2p. If I had more than 7 electrons, what will be the case in that scenario? We'll have 1s being full, no problem. We'll have 2s being full, no problem. But my 2p here might have something like 1, 2, 3, 4 and 5. It might have 5 electrons, it might have 4. But the key thing here is at least one set of paired up electrons exist. So when you're having at least one set of paired up electrons present here, let's now consider the x2 over here as the average energy per electron. The reality here is, because it is paired up, what happens is, as electron gets paired up, it has higher average energy. X2 will be greater than x1. Why? In the sense, you'll have electron having greater energy. Why will it have greater energy? Simply because it has to overcome electrostatic repulsions to pair up. So when you are saying pairing up here, right, what does pairing up really mean? So when the electron gets paired up here, it overcomes electrostatic repulsions. But what does it gain? Gains magnetic attraction. Basically, when you are having two electrons of opposite spins in the same orbital, what is the idea there? They both individually act like, oppositely poled magnets. Electron number 1 will be one type of magnet, which is north-south. The electron number 2 in the same space will be exact opposite south-north type of magnet, meaning they will effectively be magnetically attracting each other. How do you understand this? How do you use this? You are familiar, you have done what is that thing called? AC and all of that stuff. Magnetism is over in your physics?
No, not yet, sir.
Not yet. You're familiar with right hand curl rule and that type of thing?
Yes, sir.
So effectively, when you're going to be having, say, a particular electron spinning in a clockwise manner, what is going to be happening? It will basically be spinning in this manner, means you'll have its magnetic field lines going upward. So it's like you're going to be having south at the bottom, north at the top here. If you have it in the opposite spin, it is exactly in the opposite direction. So it's like south at the top and the north at the bottom. So effectively, the two electrons in the same space. When I did this and showed you, I was doing in the same space there. When the two electrons are present in the same space, they literally act like magnets in opposite directions. Which rule? I'm using right hand curl rule. Because when you're going to be having this as the, when I'm looking at electricity in this curl direction, magnetic field is straight, or if magnetic field is this way, electricity generated will be the opposite in this direction over here. That is your, you're familiar with that rule, yes?
Yes, sir.
Was I correct with my physics interpretation there?
Yes, sir.
Okay, alright. Because I've not really done that rule in a long time. Anyway, coming back to this. So, it overcomes the electrostatic repulsions, but mainly because it gets magnetic attraction happening there. So, electrostatic repulsions it has to overcome, magnetically it will have attraction. But of course, electrostatic force is much stronger than magnetic. So, when the electron does get paired up, it will have slightly greater energy. X2 will be greater than X1. So, that is going to be the case. Now, when you are going to be having this as the scenario here, what is the problem which happens because of this? The problem which happens over here is when you are going to be having more than 14 electrons. 14 electrons total. You are going to be having X2 type of scenario being applicable there. So there is no problem with respect to the X2 type of scenario there. It is perfectly fine. No issues at all. In the sense, whatever we discussed till now, all of those are perfectly clear. You are going to be having a perfectly clean off-board applicable. Whereas the problem happens when you are going to be having less than 14 electrons total. So what happens in that particular case is when you're going to be having less than 14 electrons total, you're going to be having the sigma 2pz having comparable energy. Comparable energy, or you can say they are now sharing a similar space and they have comparable energy to sigma star 2s. In a sense, which two are going to be having problems over here? Let me show it to you in this particular graph over here. You're going to be having this fellow and this guy basically becoming of similar energies. Alright, this fellow and this guy will basically become similar energies because the 2s you can say and the 2p are going to be of similar energies right now. What does this effectively lead to happening over here? what happens in this particular case is like this. Let me now give you a very, what to say, simple thought experiment type of thing. Let's say I know for a fact I'm going to die in 5 months or 6 months time. Nobody else knows this. I am the only person who knows this. If I found out for whatever reason that I'm going to die in 6 months, nobody else knows this. What will I do? I'm going to have proper full health, everything is available. I'm just going to suddenly die 6 months down the line or 10 months down the line. You'll want to enjoy that time, correct?
Yes, sir.
What would you require for enjoying time? Most important thing. Mental peace is necessary, but that is gone. Because you're going to die, so that mental peace is gone. What else is necessary? People are necessary. And most critically, currency is necessary, correct? You need money. So, ideally, let's say I'm going to be not that particularly filthy rich, but I would like to, enjoy everything which life can offer me. Then I will require money. What will I do then? Will I sit and work?
No.
What will I do? You're a sharp, clever fellow. What will you do? Will you go rob a
Let
bank?
the money go. No.
That is going to be worthless. You'll go in prison. But you'll rob a bank legally. You'll basically go get a loan. As fat a loan as you can. You will not bother with any real conditions there. You will tell them all the payments will start after 6 months or 10 months. After the time you are going to be roughly gone, start it off. No problem. I'm gone anyway. You'll have to write it off then. So the idea here is we will basically try to make our current part of time which we know for sure we are going to be present in as comfortable as possible, at the cost of making the time when we are not going to be present in as uncomfortable as it can be. So what we are trying to do over here is we will try to make the time when we are going to be alive and living properly as comfortable and as enjoyable as possible. But the time when we are gone, bhaad mein ja, I don't really care. It doesn't matter. Let it go to whatever problems it is going to be having. So that is the same type of analysis which happens in the atoms over here also. In a theoretical perspective, you can imagine it like that. So let's say I'm having less than 14 electrons total. So I'm going to be showing only the orbitals which are of similar energy here. So let's say I'm considering sigma 2s and 2s and 2s overlap and 2p and 2p overlaps here. So we're going to be having sigma 2s, sigma star and sigma 2s over here. So this is sigma 2s, sigma star 2s, and we are going to be putting up the 2p over here. So this is going to be sigma 2p and we'll have pi 2p over here and sigma star 2p. So this is going to be pi 2px, let's just call it pi 2p and pi star 2p. Okay. What happens now is, as you can see here in this kind of a diagram, and I drew it like this. I did not draw it for any other reason. I wanted to show that these two are of similar energies over here, so that you understand what is going to be happening here. So what happens now is, in this particular case, let's put the difference in energies also over here like this. Over here, this is the difference in energies. These two are different levels of differences. They are not the same. What happens now is this. You're going to be having, in this case, if there is less than 14 electrons total, that means the molecule is maximum going to get filled up only up to here. It is not going to fill this part up for sure. So what is going to be now happening is, you are going to be having an overlap. I told you already, similar energy orbitals will overlap and they can mix. That is the rule of MOT. So because you are going to be having sigma star 2s and sigma 2p of similar energies, we will technically now have 2s and 2p. In this case, 2s and 2pz are going to be overlapping orbitals over here. Or you can say sigma star 2s. Of course, sigma star 2s is overlapping now. It's complementary mathematical function. Sigma 2s also overlaps because they are both tied to each other mathematically. Why? Because 2s is defined as this space, sigma star is defined as that space. So this is sigma now, this is sigma star. So the idea here is sigma plus sigma star basically should work out as a full 0 or a 1, whatever entity you are looking at mathematically there. So sigma 2s, sigma star 2s, sigma star 2pz and sigma 2pz. These four are now going to be mixing. When I say they are going to be mixing, what is it that actually really happens over here? You can say that in the new mixed scenario over here, I should have drawn this a little bit better here. So slightly I am going to change this diagram. Sorry. Okay. Slight changes because I need to draw a few other extra things here. So let's put this over here and over here. This is still too much. Sigma 2s and this will be sigma star 2s. Okay. So let's say this was the gap over here. Now what is going to be happening now is very simple. It is simple, but at the same time it is the same as the lone nonsense which I said. If I am knowing that I am dying and I am the only person who knows that, and I know for a time how much time period I have, I will go take a loan. Make my current life, when I am knowing for sure I am going to be alive, as satisfactorily, as fun as possible, as enjoyable as possible, and throw the pain for later when I am not going to be there anyway. So what will be the thing which the molecule will be doing is going to be very similar. It will now stabilize this part over here. That is, this part and this part are mixing. So this part is for sure getting filled. This part, the top is for sure not getting filled. So this part will get destabilized and this part will get stabilized. So when you are having this part getting destabilized and this part getting stabilized, they will basically end up adjusting slightly. When I say adjusting slightly, this entire thing will move up slightly in such a way that we will now end up having this becoming the level of sigma 2pz and we will end up having sigma star 2p at this level over here. Now what is going to be the same over here? We will end up having this gap being the same. These two gaps are going to be the same. Alright, these two gaps are going to be the same in the sense, let's say I am calling this delta E1. This will also be delta E1. Okay, if this is delta E2, in the next case here, if this is getting destabilized here, how much of a destabilization is happening here? This much amount of destabilization is happening here. So let's call this X. That same amount of X amount of stabilization now happens for the sigma 2s and sigma star 2s. Meaning we will now end up having this one going down over here to a level. This will go down to this level over here. We will now have this gap being the same as delta E2. No problems there. But what will now be the extra thing here? We will now have this extra stability of X being seen in this particular case here. So the sigma 2s and sigma star 2s will go down by X. Sigma 2pz and sigma star 2pz will go up by X. So now let's say I'm going to be looking at that loan case itself. If the bank is insisting I have to pay the loan back a little bit, I will first try to push it. Let's say I'm going to die in 6 months. I will try to push it to after 6 months as much as I can. Or if they are insisting, I'll have to start at some point of time. I can basically make a deal saying I will not pay anything for the first 4 or 5 months. Last 5th month or 6th month, I'll pay some token amounts. After 6 months, after 1 year, I'll start paying fully. Something like that. That is the kind of deal I will make. In the sense, I will postpone my repayment to as late as I can. That is basically the goal there, so that I can enjoy as much as I can before I am going to be forced into some unnecessary irritation. I don't want unnecessary calls by the time I'm about to go away and enjoying in some place. I don't want to get some stupid calls from lenders and creditors. Not fun. Look at how Vijay Mallya's life has become. He had made a lot of money. He had done very good for Indian aviation industry. But what happened? When he could not pay back his loans, he got screwed badly. He basically, even though he had money, he had to basically keep bouncing and dodging calls and get so much mental pressure. So his life became very miserable. So I would not say it miserable. He's still extremely rich. I would not say he's in a miserable stage, but yeah, still miserable compared to what it probably was for that sir. So the idea here is we would like to postpone that repayment as much as possible. Now let us try to understand what that translates to over here. In this particular case here, when you're looking at it, which orbitals are getting stabilized over here? The MOTs which get stabilized are going to be sigma 2s and sigma star 2s. Both of them are definitely going to get filled up, almost certainly. So they definitely are going to be nicely stabilized. Very good. Which ones are destabilized? Destabilized are sigma 2pz and sigma star 2pz. Sigma star 2pz, I don't care. Why? Because never filled. Don't care. Because less than 14 only this kind of thing is going to be happening. Why is this only possible for less than 14? Because you are going to be having, what to say, lower energy. X1 less than X2 implies lower energy for 2p. That is the reason why you are going to be having the sigma 2pz having similar energy as the sigma star 2s here. So you would want the loan repayment to start as late as possible, meaning this is the only one which may get filled up. May get filled up. Now if this sigma 2pz gets filled up, we are now going to have to pay back a little bit of that loan over there. X amount of that loan which we have taken as benefit for our current thing, we have to start paying back. So we would like to push it as late as possible. So since it may get filled up, push it as late as possible. As late for filling as possible. What will this basically result in? This effectively results in sigma 2pz in case of less than 14 electrons total. It gets filled up after pi 2px equal to pi 2py. Ideally speaking, you don't want to incur that extra, what to say, loan payment happening over here. If you are going to be filling up the sigma 2pz now, that basically means you are basically repaying back some of the benefit which you got by filling up 2s and sigma 2s and sigma star 2s. You got benefit by filling these two, but now by filling this fellow, you are losing some of that benefit away. So you would prefer to fill it up as late as possible. So effectively what happens is, off-bow order for less than 14 electrons total is going to be changing now. What is the change which you are going to be having? You will still have sigma 1s, sigma star 1s. You will have sigma 2s, sigma star 2s. Yes, both of them are slightly more stable, but order is still going to be the same. Sigma 2s, sigma star 2s. But after the sigma star 2s, now you end up having a difference. The pi now needs to be filled up before my, what to say, sigma 2pz over there. So what will now end up happening is, we will now have pi 2px equal to pi 2py. Then we will end up having sigma 2pz. Then what is going to be present? Over here, this sigma star 2p went even more higher. The pi star 2p is actually much lower. So you will still have pi star 2p over here. One second. You will still be having pi star 2px, pi star 2py as the next ones. And lastly, you will be having sigma star 2pz. This is going to be the order of filling up, off-bow order of filling up when you are having less than 14 electrons total in a diatomic system generally. So now let's look at what is going to be meant by this filling up over here, and what are the things which we can basically extract out of this, what information we can get over here. Let's start off for something like, say, O2, which is the standard one which we have to discuss anyway. O2 had some problems there, correct? So let's understand for O2. So O2 is going to be having total 16 electrons. So how do we fill up? Each orbital gets 1 1. See, each orbital gets 2 2 electrons. So sigma 1s, then we end up having sigma star 1s, then we have sigma 2s, sigma star 2s. This is more than 14 electrons total. So I'll follow regular order. So I'll have sigma 2pz, then I'll have pi 2px equal to pi 2py. Then I'll have, instead of sigma, I'll of course be having pi star 2px equal to pi star 2py. Lastly, we should be having sigma star 2pz, but 20 electrons it is never going to reach. So let's start filling up electrons. So 2, 4, 6, 8, 10. Now, when you are filling up these two over here, you need to observe, what to say, Hund's rule in filling up. Both of them are equal energy. So you'll fill them up 1, 1 first. Check now, 2, 4, 6, 8, 10, 11, 12. So 12 electrons are only done. So we need more anyway. So finish them up, fill them up fully over there. No problem here. you're going to be having in this case 2 and 2 here. So 2, 4, 6, 8, 10, 12, 2, 4, 6, 8, 10, 12, 14 electrons are done. So 14 electrons are filled up. So the 15th electron will go over here and will end up becoming a sigma star 2px1. This looks very horribly written. I'll just put this 2 more properly here. So we are going to be having, in this case, we'll have the first electron coming here, second electron coming here. Now let's add up over here 2, 4, 6, 8, 10, 12, 14, 15, 16. So this is my electronic configuration for an oxygen molecule. And pay attention here, we had talked about how magnetic property was a complicated thing from VBT point of view. These two are going to be unpaired electrons. Because they are unpaired electrons, this molecule, O2 molecule, is of course going to be paramagnetic. If you are going to be having no unpaired electrons totally, then you are going to be calling it as a diamagnetic system. O2 molecule is a nice clean paramagnetic system because of this. Now, a couple of other points to pay attention to here. We will now be calculating something called as bond order. Bond order basically means we are just going to be doing half into total electrons in bonding molecular orbitals. So bonding molecular orbital electrons minus anti-bonding molecular orbital electrons. So let's do that for the oxygen molecule and see what we are going to be getting over here. We are going to be having sigma is going, the bonding is this 2, 4, this. So 2, 4, 6, 8, 10. So we are going to be having 10 bonding molecular orbital electrons minus anti-bonding is going to be this 2, this one and this one. So 2, 4, 5 and 6. So this works out as half into 4. This works out as 2. So the bond order basically represents number of bonds between the two atoms. Of course, there are going to be certain simple things to look at over here. When you're going to be looking at number of bonds between the two atoms, greater the bond order implies shorter the bond length. Bond length, of course, is distance between the two atoms. Bond length is distance between two atoms. And of course, greater the bond order also means stronger the bond. Implies more energy needed to break the bond. This is another way of looking at it. So stronger the bond, shorter the bond, and lastly, more stable the diatomic system. That is the idea over here. Lastly, one other point associated with bond order. If bond order is equal to 0 or negative, you can never get negative because you're always filling up only the bonding molecular orbitals before the anti-bonding. As long as you're following off-bow order, you will never get negative. So negative is meaningless actually. So no meaning in talking about negative, but 0 is possible. If bond order is 0, implies diatomic system does not exist. A diatomic system cannot exist. Now, why should it not exist over here? Because the idea here is if bond order is positive. What does that really mean? If bond order is positive, implies delta H of formation of diatomic system is going to be negative. Alright. But remember, what are you doing over here? We are always combining two atoms. That is what forming a diatomic system means. So when you are combining two atoms here to form a bond, that is like you are tying the two atoms up with a chain in between. That means delta S for this formation of diatomic system is always going to be negative. It is not going to be positive. It is always going to be negative. So for delta G, if I am going to be considering it, delta H minus T delta S. Alright, this is going to be negative. This part over here is going to be negative of negative, meaning this becomes a positive. Why is this becoming a positive? Because this delta S is going to be negative. So the entire thing will become a positive. So if delta H is not negative, implies if delta H is non-negative, implies delta G is not negative, implies it doesn't happen. That is the idea over here. So when you're going to be having bond order being equal to 0, diatomic system cannot exist is the general principle which we are going to be applying in these kind of cases over here. Okay, so bond order greater means shorter the bond length, stronger the bond, more energy need to break the bond, more stable the diatomic system. And another thing to look at over here, if I'm going to be having something like say N2 molecule, N2 is the boundary case there, correct? N2 is going to be having 14 electrons total. So what is going to be the system's configuration? Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. You will have in this case sigma 2pz will be coming out first. 14 electrons, you can use either more or less, I don't care, it doesn't make a difference. So we will use less over here to just see what is going to be happening. So pi 2px2 equal to pi 2py2. Then we'll have sigma 2pz2. If I had more than 14 electrons, what will be changing? These two will interchange, that's all, nothing else. So more than 14 electrons, the only difference between the two of them is you're going to be having an interchanging between these two over here. So let me see where I was putting that nonsense up. Yeah, so as you can see here, this is for less than 14 electrons total. More than 14 I didn't put up over here, so let me put up for more than also. More than 14 total. What will be the order? We'll have sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Then we'll end up having sigma 2pz. Then we will end up having pi 2px equal to pi 2py. Then we'll end up having pi star 2px equals pi star 2py. And lastly, we will end up having sigma star 2pz. Meaning what has interchanged between these two is this fellow and this one's location, they are basically getting interchanged. That is the idea in this case here. So for the two different levels, you're having only two parts getting interchanged, not two full segments over there. So in this case here, we'll end up having this as the order for N2 over here. One set of questions can come over there is, will N2 end up preferring to form N2 plus or N2 minus? So how you go for it is, you go for always preference is to increase bond order. Alright, so in this case here, N2, if it becomes N2 plus 1, it is going to be having bond order as, in this case, let's check out over here for an easier example, not N2, we'll take for O2 and discuss this first. Then we'll come to N2 again, because N2 is a slightly more trickier case here. So O2 we have already seen, the order is sigma 1s, sigma star 1s, sigma 2s. So 2, 2, 2, sigma star 2s. Then we'll end up having sigma 2pz2, pi 2px2 equals pi 2py2. And we'll end up having pi star 2px1 equals pi star 2py1. This is the order for O2. Bond order also we saw that it is going to be coming out as 2. How? Because we had it as half into 10 minus 6. Now if I am going to be considering O2 plus 1 or O2 minus 1, what will O2 try to become? How to decide that? How to decide that which is more feasible for O2 to become? You basically now remove the electron and check out the bond order. Bond order for O2 plus 1. Where are we removing electron from? We'll remove it from this fellow here. This is the last fellow here off bow wise. So we'll remove from an anti-bonding. So if it's going to be O2 plus 1, the bond order for it is going to be something where this 6 will become 5. So we'll end up having bond order working out as 2.5, which is of course going to be half into 10 minus 5. Whereas the same thing for the O2 minus 1 means we'll have one extra added over here or over here. So if I'm going to be having one extra added in one of these two here, my anti-bonding we are having one extra electron there. So we'll now have it as bond order working out as half into 10 minus 7, which works out as 1.5. So we are going to be having, in this particular case here, O2 plus 1 is going to be having bond order as 2.5, whereas O2 minus 1 has bond order as 1.5. So if I am going to be asked, what will O2 prefer to become? O2 prefers to become O2 plus more than O2 minus. Why? Because delta S is approximately the same in both cases. Delta H though is going to be slightly better off for the O2 plus there compared to the O2 minus. So delta G is better. So you end up having this as the case over here. Now we'll go for N2 case here. N2 here is going to be having bond order here. Let's calculate the bond order of for this fellow here. It works out as half into, what are my bonding molecular orbitals? 2, 4, 6, 8, 10. So we're going to be having half into 10 minus anti-bonding are 2, 4, nothing else. So half into 10 minus 4. So this works out as 3. So bond order is 3 for N2 here. So if I'm going to be considering this N2 here and understanding what this N2 will try to become over here. N2 can become either N2 plus or N2 minus. Now if it's going to be the case of N2 plus here, what is going to be the bond order? It will work out as half into N2 plus. Now we are going to be removing from this sigma 2pz here. So let's say I'm removing that electron from that. That means one of my electrons is removed from the 10 over here. Meaning it ends up becoming half into 9 minus 4. This works out as 2.5. In the case of N2 minus, what is going to be happening here? We are going to be adding an electron into a pi star 2px equal to pi star 2py here. Alright, so we are going to be adding an electron into this over here. Meaning extra anti-bonding electron is going to be coming up over there. So how to proceed for that over here? In this case here, we are going to be adding an electron onto the 4 here. So it becomes half into 10 minus 5. So this works out as also 2.5. So both cases bond order is same now. Now what do you prefer? Lesser number of total anti-bonding molecular orbital electrons is more preferred. So this is more preferred. Why? Because lesser number of total anti-bonding molecular orbital electrons. That is the idea in this particular case here. So of course you'll have to try this out for many different cases. One common case which is going to be seen as an interesting case is O2, N2, NO, B2, C2. These are all standard interesting cases. Why B2 and C2 are interesting? Mainly because they will have less than 14. For instance, for B2 over here, what will be the order over here? You'll end up having it as 10 electrons total for B2. So less than 14. So we'll end up having the order being sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, but then we'll have pi. So we'll now have pi 2px1 equal to pi 2py1. Alright, so you're going to be having B2. What is the speciality about B2? B2 is going to be paramagnetic as well. Even though you expect it to be diamagnetic, it is actually going to work out as paramagnetic. Now let us talk about C2 as well quickly. C2 is going to be 12 electrons, less than 14 total. Meaning in this case it works out as sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Then we'll have pi 2px2 equal to pi 2py2. So your 12 are done. Bond order in this case works out as 2 as normally expected. Alright, but one interesting thing is you will be having this as 2 pi bonds over here. Technically speaking, both are pi bonds here. There is no sigma bond technically, which is, or no sigma bonding molecular orbital type of thing, which is to be considered in this case here. So we think of it as 2 pi bonds here, not a sigma technically. Why? Because the bonding molecular orbitals which are going to be contributing to the bond order are basically pi bonds over here, not the sigma fellows there. So this is another interesting type of question which can be sometimes asked over here. NO, what can you be asked? What does NO try to prefer becoming? NO is going to be having 15 electrons total. So we'll be using more than 14 electrons order. And NO will try to become NO plus as much as possible. Why? Because NO will have bond order as 2.5, but NO plus will have bond order as 3. So NO plus is technically more stable than NO because it has a higher bond order. So these are some simple straightforward questions which can be asked in terms of MOT over here. What are the parameters to pay attention to? Magnetic means what does it mean? If they are asking you what does one system try to become? Does N2 become N2 plus or N2 minus? What do you go for? You go for the fact that N2 here has to basically become N2 plus. Why? Because of this kind of a condition. Similarly, does NO become NO plus or NO minus? NO will try to become NO plus because bond order increases in that direction. So what does bond order mean? What does it result in? Bond order means shorter bond length, number of bonds between the two bonds, shorter bond length, stronger the bond, more energy needed to break the bond, more stable the system. All of these basically are going to be dealing with the bond order aspect here. So any other parts in MOT which you have doubts in, dude? Any other bits or pieces which you have generally had problems with MOT? Anything else? I'm guessing most of what you need is covered off. Any other bits and pieces which I've forgotten to discuss?
No, sir.
You're clear with MOT to a good extent now. Why the order is changing, all of that is properly understood.
Yes, sir.
You have to memorize the two different orders for more than 14 and less than 14 ideally. Not much to memorize, but yeah, some small bit is there to memorize. This part, don't make a mistake in terms of that confusion there. That will lead to trouble. Yeah, that's basically it. I suppose we will end the discussion on MOT now then.